So we are almost done with categorizing our observations of the solar system so that when we come up with a theory, we can apply it to these characteristics and see if the theory adequately explains the characteristics and the observations that we've made. So we've talked about disk shape and the planetary types and space debris and how that debris is so important because it provides a source for composition of the solar system via spectroscopy and for age of the solar system via radioactive dating. Now we're going to finish up by looking at debris from the outer solar system, and that debris includes comets, and we've already reviewed dwarf planets from the Kuiper Belt. So we're going to look at comets now. Let's get into it. Comets are so cool, and when we look at comets, and this is a very exaggerated drawing here, when we look at comets, we can relate them to meteoroids, because when we see meteor showers, like the Perseid meteor shower in August, or the Orionid meteor shower, which is actually on now, but not as dramatic as the Perseids, when we see those meteors, those are actually debris from comets breaking up as they revolve around the sun and cross the Earth's revolutionary path. Now, comets are not in the ecliptic at all, and comets can be divided into where they originate, but wherever they originate, they're not on the ecliptic. And so this is quite exaggerated in its angle, but as the comet comes around, let's start at 1. As it comes around the sun, it starts to break up as a result of the heat of the sun and as a result of the radiation pressure and the solar wind of the sun. So the comet starts to break up. We'll talk about what the comet's composed of shortly. And as it goes past the revolution of the Earth here, it will leave debris in its wake, in its path, and that debris will hang out. And as the Earth revolves around, we will start to see that in terms of meteor showers. Meteor showers seem to come at us from one spot in the sky, and that is actually the spot where the comet intersected our revolutionary orbit. So that meteor shower is formed from the dust, the debris of the comet breaking up as it rounded the sun with the gravity and the heat and the solar wind. Let's talk about what is broken up and what that debris is. There are basically two parts to a comet. There's an icy part and a rocky part. And the icy part can really be related to the ices that we were talking about in the Kuiper Belt. Remember, Pluto is an icy planet, and those ices are not just water, although they can be, but other liquids can freeze as well. Carbon dioxide can freeze. That's what makes your dry ice. Carbon dioxide freezing, and carbon monoxide can freeze, methane can freeze, and ammonia can freeze. Those are the popular ones that you might find that are associated with the rock of a comet. A comet is not big. Literally, we're talking about, most of the time, it's a meter or so in diameter. But we've already talked about how a gram can produce a meteor in our atmosphere. Comets don't get to our atmosphere, so that meter diameter is essentially forming this brilliant light in a vacuum of space by breaking up that debris. Let's talk about that a little bit more. When we're talking about short period comets, they will orbit the sun more frequently on a less than 200-year cycle, like Halley's Comet, like Swift-Tuttle Comet, like Kohoutek that you might have heard about. They are coming in from the icy Kuiper belt. They're coming around the sun, and the sun will heat up the ices. There's volatile debris from the solid ice that is melting to liquids and vaporizing to gases, and that debris is coming off. And they are also being impacted by solar wind, which is impacting the rock of the comet in the meter size. And they're also being impacted by the gravitational pull of the sun, which is dissociating the ionic and the covalent bonds in the solid, in the rock. So you have quite a source of debris there, and the debris can be ionic debris, and it can be debris from the rock as well. Let's go into that a little bit more before we go into that. There are also long-term comets. We had short-term, less than 200 years for an orbit. Long-term comets come in like once every millennium. They come in from the outer solar system in a cloud that's beyond the Kuiper belt, and this cloud is called the Oort cloud, beyond Pluto, beyond the Kuiper belt by far, into the Oort cloud, which surrounds our entire universe, surrounds our entire solar system, whereas the Kuiper belt surrounds it in a belt. The Oort cloud surrounds it in a sphere. So comets from the Oort cloud can come in from anywhere, and they have very strange elliptical orbits as they come in, maybe on a millennium or a 10,000 year schedule. Let's get back to what you see and the debris. So there can be ionic tails from the volatile gases that are now being melted and vaporized as you go around the sun, and dust tails from the rock, which is being pulled apart by the gravity and by the radiation solar wind. That is why you can definitely see two tails, sometimes with the naked eye, when it comes to a comet. And one of the tails might just curve, the dust tail might curve because it has more mass to its components. Obviously, the solid carbons in the rock have more mass and are more massive than the gases. And because they have more mass, they don't get shot out away from the sun directly. They can form a curve. So you can have two tails to a comet, and one of them can seem to curve. You're not seeing things. It's actually the way it can be, especially if you look at it with your telescope. So again, our observations are that our solar system has a disk shape to it and an ecliptic. Our solar system has two planetary types. They are the terrestrial types closer to the sun and the gaseous and liquid types that are farther away from the sun. We also have dwarf planets that are icy, smaller sectors farther away from the sun. We have space debris that are the home for some of those dwarf planets, and space debris that is out in a cloud around the entire solar system. And from this debris hitting the Earth, and from moon rocks that we pick up off the moon, and from volcanic explosions which bring out the magma from the core, bring out the magma from the mantle of our Earth, we can come up with a common age of about 4.5 billion years for our solar system. Now, we're going to look at theories, many, many theories, about how our solar system originated, and we're going to line them up with how much they explain these characteristics. I'll see you on the next one.